Vin Future Prize, a new global science and technology prize for humanity from Vietnam. One Vin Future Grand Prize of $3 million. Three additional special Vin Future Prizes valued at $500,000 each. Vin Future Prize honors science and technology work that creates or has a high potential to create meaningful change in the everyday lives of millions of people. Join us to make a change for a better future.
Okay, now we can start. Welcome again to the Vin Future Public Dialogue. Imagine a dog facing a fence that is too high. If the dog cannot jump over that fence, he turns back. However, humans can become the high fence in many ways. One of the ways is to use a hammer to knock down the fence. So humans' abilities to use tools and materials help them survive and create their civilization. That's what I learned in the philosophy course when I was a student in Russia. We all know that materials and energy are an essential part of our lives, but how to store energy, how to create future materials, and finally, how to transform energy and materials research into industrial production. To discuss with you these questions, we have invited today the three brilliant minds in science and entrepreneurship. Welcome to you all.
In response to the global energy crisis, researchers and scientists around the globe are opening the door to a future world built from brand new materials and powered by energies that will never exhaust. How could this be real? Let the top global scientists and prominent startup entrepreneurs tell you the stories of how scientific innovations have brought smart materials and sustainable energy into changing the current lives and shaping the future. In the Vin Future Public Dialogue Number 2, Renewable Energy and New Materials for the Future. For the first time, young scientists and science enthusiasts in Vietnam have the opportunity to talk to the youngest Nobel laureate in physics ever since 1973, Professor Konstantin Kostya Sergeyevich Novoselov, and discover his achievements of graphene, the strongest ultra-thin material in history. The world of renewable energy will become much more lively and vivid with the inspiring conversation from Professor Thuc Nguyen Nguyen, the pride of Vietnam in the field of material sciences, as well as one of the world's most influential scientific minds in 2019. Dr. Corey Hoven, scientist, founder, and CTO of Next Energy Technologies, will give you an example of successfully commercializing smart solar-powered windows that can generate electricity for high-rise buildings. The dialogue will take place via Zoom and be live-streamed on the official fan page and YouTube channel of Vin Future Prize at 8:15 a.m. Vietnamese time on November 12, 2021.
Very much welcome back. One of the missions of the Vin Future Public Dialogue series is to create an enjoyable conversation where the daily curiosity of the public meets the fundamental curiosity of the keynote speakers. Please leave your questions at the Q&A box and we will invite you to directly ask questions to the keynote speakers. Now, please allow me to walk you through the agenda for today. After the welcome remark from the Vin Future Foundation, you will meet our first keynote speaker in the topic, how has solar cell and energy changed our lives so far? The next speaker will bring us an exciting talk on materials for the future, followed by the third speaker on transforming materials and energy research into industrial production. Finally, we will enjoy the ideas presentation of young scientists and startups, accompanied by the advisory support from the keynote speakers. And we will close the dialogue with the Q&A session with the public. In a moment, I will introduce to you the keynote speakers, but for now, I would like to invite Dr. Lê Mai Lan, the Vice Chairperson of Vingroup and designated representative of the Vin Future Foundation, for her opening remark. Please welcome Dr. Lê Mai Lan.
Thank you. Ladies and gentlemen, hello and welcome to our Vin Future Public Dialogue. Breakthrough invention by a famous scientist have changed the world. However, rapid economic development is not always favorable. It also has negative consequences on quality of life, such as climate change, air pollution, epidemics, inequality, and so on. Therefore, VinFuture Foundation is calling for future innovations which promoting economic development, but at the same time, protecting our planet and our environment. What we do today could transform the life of tomorrow's. The type of energy we produce, the ways of material we use, will shape the future for us and for our next generation. Hence, on behalf of the Future Foundations, I would like to thank you for your interest in today's dialogue of renewable energy and new materials for the future. I would like to thank the keynote speakers for your tremendous contribution and the VinFuture team for helping to put together this event. I wish you a great time and thank you once again.
Thank you very much, Dr. Lê Mai Lan. And now, I'm very nervous to introduce to you our very first speaker. Born in Vietnam and achieved tremendous success in the United States, our very first keynote speaker and our pride, Professor Thục Quyên Nguyễn, is now the chemistry professor at the University of California in Santa Barbara. She's among most influential scientists in material science. And I have the privilege to assist Professor Quyên at the VinFuture Foundation. And I admire her belief about science and technology. She once said, there are excellent technologies in the world, but they are way too expensive for poor people. Our mission is to make technologies affordable for the poor. Please welcome Professor Thục Quyên Nguyễn.
Thank you very much, Minh Anh. So may I share the screen, please?
Please.
So good morning, good afternoon, and good evening to our participants. Thank you very much for joining us today. And before I start, I would like to thank Dr. Mai Lan and also Dr. Minh Anh for organizing this event and all the technical support staff. And thank you very much for having me part of this team today. So today I would like to talk about how has solar energy changed our lives so far. And so the first question I have for you guys is, do you think energy will be the future challenge? And so you can type quickly just yes or no in the text box. I give you just a few seconds to do so. Okay. So if you answer yes, the energy will be a future challenge, and we will see why. So the current global energy consumption is 17.7 terawatt. Projected consumption in 2050 is around 28 terawatt, and it's due to population and economic growth. So let's take a quick look and see why population and economic growth will cause the future energy challenge. And let's take a look at the world population. The current population is about 7.8 billion people. And so it took over 2 million years for the world population to reach 1 billion, but only 200 years or so to grow up to 7 billion. And let's see why the growing population will cause the future energy challenge and also other issues like Dr. Mai Lan already mentioned, also about the climate change. So let us take a look at the energy consumption in the past. Let's go back to 100 years ago and get to see. So back then, for cooking, people gather branches or they use coal and they make a fire and to cook. And so if you look at the photo here, so if you kind of consider that wealthy, so you have the stove like the one I show in the photo here. People did not have a fancy gas or electric stove where they turn on the knob and they could cook. And then if you are poor, you actually use the clay stove and you burn the coals or branches and you use for cooking. And for transportation, besides walking by foot and people use horse carriage, or they travel by boat. And for lighting, people use oil lamp or they use the kerosene lamp. And actually, I grew up in villages in Vietnam, and this was how my family cooked. And we use oil lamp for pretty much 16 years of my life. We have very little access to electricity and also the kerosene lamp. And this was a photo of me when I was 16, and you can see the very dim oil lamp hanging in the back. So now let us step back to the present, and this will help us to see why energy will be future challenge. So nowadays, many of us, we own electronic devices, and the computer, cell phone, TV, and at home we have dishwasher, stove, the refrigerator, and many other appliances, right? And so each type of these electronic devices, they can consume certain amount of energy. And for transportation, people drive by car, bus, train, and airplane. But a big portion of our energy go into lighting. So all of these will contribute to the future energy challenge. As the population grow, economic growth, people can afford a better lifestyle and they can own many more things. And so we enjoy the modern world with electricity, but do you know there is still a large world population living now without access to electricity? So in 2010, there were 1.2 billion people in the world that did not have access to electricity. So in 2019, this number now reduced to about 750 million people. And around 600 million people live in Africa still do not have access to electricity. And actually in the highland area, villages in Vietnam, that they did not have access to electricity. And I think even though to this day, there's some people still do not have access to electricity. So we see that electricity changed our lifestyle, but it also create problem. And the problem is that if we look at the current energy consumption from different parts of the world, I got the plot here, you can see majority of the energy consumption is dominated by non-renewable energy sources. And that will lead to the climate change, right? And so to cap the carbon dioxide at this level, most of the additional energy need for 2050 must come from carbon-free sources. And we look around us, there are more than one type of carbon-free energy sources. But the solar energy by far is the largest carbon-free energy source and can provide up to 100,000 terawatt. So the past 50 years, I think people aware of the future energy challenge. And you can see people have been doing research on different solar cell technology for the past 50 years. So I got the plot here to show you different type of solar cell technology have been developed over the years. Some of them extremely efficient, but they're very expensive. And some of them less efficient and lower cost, right? And so if we see how the solar energy changed our lives so far, and you can see here, I put here a number of different photos that from people in Africa. So they cannot afford to have many solar cell modules. Sometimes for the household, they can have only one module. And they make it really portable where they can move the module around and charge during the day. For example, here, they use to charge the battery and they use to power a laptop or charge the cell phone. And so the gentleman here tried to arrange it to charge the battery for cars. And they also can move it around and use to power a water pump. But most importantly, that really helped change the people lifestyle, also the solar power light, okay, that people can use at nighttime. So this very clever design where they have the portable solar power lamp with the small battery in there that they can use for study at night. Okay? And if without the solar lamp, people have to use kerosene lamp, or they can have wood fire. And this really released the carbon dioxide to the environment and also affect human health and also cause the climate pollution and also climate change. And so here I also show another application where they can use silicon solar cell module and organic solar cell module to use for greenhouse, to power the temperature control unit for the greenhouse. And if you grow your vegetable using the greenhouse, you do not have to spray chemical. Okay? And so that's really good for the environment as well. And then here I show the two photos in the bottom. One they used by Mongolian horse breeder because they live in the wilderness and they live in the tent. And so they need the portable solar module. And the one on the right that they use to power the refrigerator and to keep the vaccine cool at low temperature. Okay? And so beside they are silicon solar cell, there are also other new type of solar cell technology that can be made flexible, lightweight, and portable. So for example, the really pioneer work by Takao Someo from University of Tokyo in Japan, that where he actually fabricate solar cell on fabric, and then they wash it and they can be able to use it. And then you can see here the installation of some of this organic solar cell module can be very fast and simple. So I just hope that I kind of show you a quick snapshot of how solar energy can really change our life. And thank you very much for your attention. I look forward to the Q&A section.
Thank you very much, Professor Quyên. So I understand that what we learned from you is that there's still around 760 million people in the world now without access to electricity, and there's a lot to do in this matter. And our future may rely on the organic solar cells. I believe it's one of the good things. Very, very nicely. I would like to let you know that we now in this Zoom call, we have more than 300 people following us. And we have other people watching us on YouTube and the live stream on our Facebook page. And there are many young scientists, university and high school students watching us, and they will ask a lot of questions, so be prepared. Thank you very much again, Professor Quyên. So now I would like to go to the next our speaker. This Russian-born scientist has been a phenomenon in physics. Professor Konstantin Sergeyevich Novoselov, or as he would like to be called, Kostya Novoselov, holds the professorship at the National University of Singapore and the University of Manchester. Together with his teacher, Professor Novoselov successfully produced the two-dimensional material graphene in their groundbreaking experiments. This discovery brought them the Nobel Prize in Physics in 2010. Since 1973, Konstantin Novoselov has been the youngest Nobel laureate in physics. Please welcome Professor Kostya Novoselov.
Good afternoon, good morning, good evening. It's really a great pleasure to be here, and I would like to thank for this invitation. It's really a fantastic opportunity, and it was really a great pleasure to work in this Win Future Prize. But also it's really great to see that we are open not only to the established scientists but also to the young researchers as well, and to the future researchers. So really great thanks to Milan and to Minan. And I'll try to be brief, and would like to pose a question. So what would materials which we will use in the future will look like? We think that what we've got now will be with us forever, but actually history teaches us that the dominant materials do change as we progress in our development. We even give names to the times we live in by the names of the dominant materials. Like we all learned in school that there was a Stone Age, and then the Bronze Age, and then the Iron Age. And a good question would be, how do we call the current age, which when we live in? And quite interestingly, that probably for the first time in history, we now have a choice, and it's quite a broad choice. We can call our time the digital age, maybe, or the silicon age, or maybe even the nuclear age. So, but what it is also obvious that first of all, it's probably good to make a smart choice, but maybe we need to pause a little bit, and maybe we need to ask ourselves, do we need to make a choice, and do we need to select the dominant material? Let me explain you why. What do I mean by this? So here is the periodic table of elements which we used in our silicon technology prior to 1990. So there is silicon, boron, phosphorus for doping, aluminium for interconnects, hydrogen, oxygen for passivation. Extremely simple, very simple technology. Even I could probably master. Then a few years later, the density of the transistors started to grow, and we started to put more and more of those transistors together. We needed to make the wires, the interconnects, thinner, more narrow. So we started to use copper instead of aluminium. So if you use copper, you need to use some work function matching materials, maybe some diffusion barriers. So we added a few materials like tantalum, tungsten, titanium, germanium, copper, but it's still reasonably manageable. If you look at the silicon technology these days, we basically use more than half of the periodic tables in our silicon chips. So we started with a very simple, very understandable technology, and these days it's really every single fab is a multi-billion investment, and it's all because we keep betting on the same material, on silicon, even trying to use it beyond its capabilities, and we keep adapting it for the new requirements. And the situation is actually quite bizarre, because if I compare the number of elements we use in our body, in human body, and the number of elements we use in integrated circuits, you would see that it looks like our silicon technology is more complex than our cells. And I hope you would agree with me that as humans, we're still more versatile. We still can do some of the tasks better than our silicon friends. So what I'm arguing is that unfortunately we as humans, as humanity, we decided to bet on only few materials, which is good. We know them really inside out, but at the same time, it really limits our capability. So all our electronics based on silicon, all our construction depends on the strength of the steel. Aerospace engineering, it's aluminium, a little bit of titanium. So we really are slaves of those few materials. If any engineer would like to create a new device, he or she would need to go to look what silicon can do for me. Was the band structure, was the band gap, was the work function, and then design a material within those constraints. So, but of course, ideally, you would like to escape from this, and we do know how to do it. We create composite materials, heterostructures, and we start using those in many applications, but it's still few, and and far between. So ideally, you would really like to disconnect from the properties of materials and depend on the particular application. Depending on the particular application, you would like to grow a new material on demand for every new application, for every new device. Then you can design very specific structure. You can assign functionalities to different layers, and then you can actually tune the properties so it will be very, very suitable for a particular application. And that's what Professor Nguyen just has been talking about, that silicon is great for photovoltaic, but maybe in some applications it's actually much better to switch to other materials as well. And so I would like to discuss these opportunities, the opportunities which are given to us by the fact that we now can create new materials on demand for new challenging applications. Thank you.
Thank you very much, Professor Novoselov. As we understand from your presentation that we use more and more chemical elements in producing materials for the future, and the good thing is we don't depend on the materials that the nature offers anymore, and we can create materials and make choices of materials, right?
Correct. Yes.
Yeah.
That's exactly what we would like to do, is really to disconnect from what nature can offer us and create our own on-demand materials for new applications.
Yeah, this is awesome. Thank you very much for that. We have enjoyed the amazing science from Professor Nguyen and Professor Novoselov. How about transforming materials and energy research into industrial production? For this, I would like to invite our next keynote speaker. Dr. Corey Hoven is the founder and CTO of Next Energy Technologies. Dr. Corey Hoven is the scientist and entrepreneur holding a PhD in materials engineering. His company focuses on beautiful windows that generate electricity for buildings. Please welcome Dr. Corey Hoven.
Hey, thank you very much. I'm Corey Hoven. I'm the CTO and co-founder of Next Energy Technologies. So first, I would like to thank the VinFuture Foundation for the invitation. So today, I'm going to be following up with these great presentations by providing an example of transforming materials and energy research into industrial production. So at Next Energy Technologies, we've developed windows that look like normal, beautiful windows, but they generate energy using transparent photovoltaics. So this game-changing renewable energy technology was based on brand new materials for the future. The technology came out of the labs of great scientists, including Professor Quinn Nguyen, whom you heard speak earlier. And so here's the problem we're trying to address with our materials and technology at Next. So buildings consume 40% of the world's energy. Now, if you're looking to make an impact on climate change, you're not going to find a bigger lever than this. And it gets crazier. By 2060, global building stock is anticipated to double. That's the equivalent to adding an entire New York City to the planet every 34 days for the next 40 years. Not surprisingly, there's also a lot of interest in dealing with this problem. And we're seeing that being addressed in many ways, including regulations, where we're seeing new codes and mandates around the world calling for net zero buildings. So these are buildings that do not consume energy. So if you want to address this problem, the big question is, how do you make energy producing buildings? An amazing amount of work has been done to make buildings more efficient, such as LED lighting. But the missing piece of the puzzle to make them net zero is on-site renewable production, where there's currently limited to no options. So as you can see in this picture, there's not necessarily a lot of rooftop space for conventional photovoltaics in commercial buildings. On the other hand, there's a lot of space on the facades of the building where the windows are located. So the answer is obvious. It seems obvious. Let's make photovoltaic windows. Well, that's not so simple. Every photovoltaic currently on the market is non-transparent. Now, this is obviously not an ideal property for a window where the entire value proposition is its transparency. To be fair, people are making photovoltaic windows, but they're in one way or the other distributing non-transparent photovoltaics across the window. This is a tough approach for market adoption as they're not attractive windows. So as a company trying to transform material and energy research into industrial production, we spend a lot of time as needed understanding our customers. What we've learned is that in this market, aesthetics is everything. So the other problem with the technologies currently on the market is they only generate energy in the locations that have non-transparent photovoltaics. So this is where we've come in, and we think we can change the world with a new material technology. So at Next, we've developed windows that look just like normal windows, except they generate energy. So we do this by harvesting primarily the infrared, the IR, and the ultraviolet, the UV light, while allowing visible light through. So the IR and UV light is light that the eye cannot see, and it's actually undesirable to enter the building. So this ability to harvest the IR and the UV light by letting visible light through is not something you can do with any photovoltaic technology currently on the market. This ability is enabled by the organic semiconductor, a material that has been extensively developed by Professor Quinn Wynn, who you saw speak earlier. The organic semiconductor was invented at the University of California, Santa Barbara. Professor there, Alan Heeger, received the Nobel Prize for that invention. It's also the core technology behind OLED televisions, where the O stands for organic. And by organic here, we just mean it's a carbon-based semiconductor. So these core materials, these organic semiconductors, have some really unique properties. Quinn showed some of them earlier. And one of them allows us to harvest IR light while allowing visible light through. And actually, these can be developed at different colors and different light transmissions. But our first product we've developed perfectly matches the color preferred by architects and matching some of the top selling window products in the commercial building market. So in addition to providing a solution to the problem of on-site generation for commercial buildings, as we discussed, it turns out this approach has some other really amazing benefits. So interestingly, most of the cost of this technology are already paid for in the window. It turns out that windows and photovoltaics are almost the exact same thing. Other than the fact that windows are defined by their transparency and photovoltaics are not transparent, by material composition, they are mostly the same. While photovoltaic panels clearly have a photovoltaic module in them, most of the material in the panels is two pieces of tempered glass, an inner layer and a PIB edge seal. All of these also exist in a window, so the additional cost to add this technology to a window, of which someone is already buying, is very low. So in addition, the other costs associated with installing a photovoltaic module are also reduced or eliminated. So in the solar industry, these are called the balance of system costs, and they include the frame to support the photovoltaic, installation costs, etc. They're typically actually around 2 times greater than the cost of the module itself. But by integrating into a window, you are removing or reducing many of these costs as well. Someone is already installing them. There's already a frame in place. So here's an example of a few demonstration walls we have done where our photovoltaic windows have been integrated into a mostly conventional framing system. So the wall on the right is located here at Next and uses a Conyers framing system, which is one of the most popular framing systems in the world. While the one at the left is now located at the headquarters of Bouygues Construction in Paris, which is one of the largest construction companies in the world. And it was framed by Walters and Wolff using a framing system specifically designed for photovoltaics. So it made the installation a little quicker and lower cost. We have another demonstration wall going into Walters and Wolff this month, and another going into building in the next few months. So these are all operational. The other really exciting thing about the materials and the technology in terms of transforming it into industrial production is that it is very well suited for integration into the supply chain. We like to say that we are disrupting the world without disrupting the supply chain, and we think that's very important for speedy market adoption. So we spent time making sure we integrate at the right spot in the supply chain, that we remove barriers throughout the supply chain, and we motivate and make wins for everyone in the supply chain. So the supply chain works like this. It starts with an architect who specs a product. As I mentioned, they care about aesthetics, who have spent a lot of time understanding exactly what they want. In fact, we have Andy Cohen, the co-CEO of Gensler, the largest architecture firm in the world, on our board of directors. So that spec is passed then to the flat glass manufacturer, who basically makes large sheets of glass. There's a handful of them in the world, and they make their best margins on glass that has advanced coatings already on them that reflect the IR and UV light. So we're also already working with a number of those, and then they take that glass and they sell those large sheets of glass to glass fabricators. The glass fabricators cut the pieces of glass to size, heat strengthen or temper the glass, maybe laminate the glass, and make a window called an insulated glass unit. The glass fabricator is where our technology has to be integrated. As mentioned, our technology goes between two pieces of glass, and so that's why we really need to integrate right here. So the business model we're using is to provide basically a turnkey solution with the necessary manufacturing equipment to existing glass fabricators for them to produce and sell next photovoltaic windows, and we can make our money from royalties and ink sales. Again, this allows the market to kind of operate as it has, establish relationships to exist as it have, to really allow this to kind of spread out into the world as quickly as possible. So we've already partnered with Viracon, the largest glass fabricator for commercial buildings in the United States. Now we're really looking to replicate this model throughout the world. That said, we are building a flagship production line ourselves that'll allow other fabricators to come and kick the tires and take some product off the line to seed their markets while their lines are being built. This will be our first production line. So this business model is really enabled by the material and the technology. So the other really exciting thing about these materials in terms of transforming into industrial production is that our organic semiconductors we've developed can be printed from ink. This allows for low-cost production and capital equipment. The cost is on a scale that the glass fabricators can afford. It makes good economic sense for them. So if we used instead more traditional methods for making solar, such as sputtering, this would not be the case, and there would be a huge barrier to supply chain integration. So the next step on the supply chain is the glazers. So they buy the insulated glass units from the fabricators. They're the companies that put the frames on and install it. Obviously, this is a critical step for the adoption of this technology. As shown in the previous slide with the demo walls, we've already been working with key glazers in the US to make sure this goes as seamlessly as possible. From there, the glazer actually sells these to the business owner, the building owners. This is the end customer. This is whose problem we're trying to solve. This allows them to meet codes, certifications, mandates, and it allows buildings to become net zero. So with that, I would just like to thank everyone for their time. Again, thanks to the VinFuture Foundation and invitation for hosting. Looking forward to answering questions in the Q&A session.
Thank you, Dr. Corey Hoven. Thank you very much for this very useful information. Now we are turning to a very exciting session of ideas, presentation of young scientists and startups, and followed by the advisory support from the keynote speakers. We have two projects coming in, and the very first project is increasing efficiency, power density, and reliability of the power converters in renewable energy applications. And I believe that the startup owner, Mr. Trần Ngọc Hải, is here. So Mr. Hải, can you directly pose your question to our keynote speakers, please?
Hello, everyone. It's a great honor to be here today. Thanks for VinFuture for invitation. So I'm Hải, founder of XAVTech Vietnam. So our company is a research and development company. It just founded in this year, 2021. And our mission is focusing on the design of high power density and high efficiency and reliable power converter for electric vehicle, including onboard battery charger, DC fast charger, low voltage battery charger, and traction inverter. So as we can know, like the next generation of electric vehicle require the car with the longer driving range, which could be like 1,000 kilometer driving distance on a single charge. So this requires the larger battery energy, which leads to larger battery volume. However, the car's volume and footprint is limited. Therefore, to increase the battery energy, the volume of other components, such as motor or power converters, must be reduced. Although the volume of these power converter must be reduced to give us spacious enough for large battery, their power rating is increased significantly to achieve the customer satisfaction. So as a result, the significantly increasing the power density of power converter in the electric vehicle becoming challenging. And it is a very hot topic nowadays in the power electronic community, and also this is our company interest. So to increase the power density of the converter, the key solution is we have to increase the switching frequency. So, however, increasing the switching frequency is caused two problems, which is the loss in the semiconductor device increase proportionally with the switching frequency, and also the loss on the semiconductor device, the loss on the magnetic device, which is inductor core and transformer core, also increase with the switching frequency. So my question for the professors presenting today is, because we are working on power converter design, so we are interested in the new material of semiconductor device and magnetic device. At this moment in our company, we usually use ferrite device and wide bandgap device for these components for magnetic and semiconductor. So, and I would like to ask, like, is there any better candidate compared to ferrite-based material for magnetic design?
Right.
Because for magnetic design, for ferrite material, we use the switching frequency at this moment. We are limited at around just several megahertz. But the requirement nowadays can be up to more than 10 megahertz or several 10 megahertz. So and the availability of these magnetic material is very, very limited. So I would like to know, is there any better candidate or promising material to replace ferrite in this in the material viewpoint?
Yeah, thank you, Hai. Thank you very much. I think that Professor Quinn can take lead in answering to some of your concerns and requests, and then people can join in. Thank you. Please, Professor Quinn.
Thank you for the question. You're absolutely right that the theme have been occur again throughout the public dialogue, that the importance of finding alternative material. And so basically, for semiconducting material, I think there are a lot of interest in using synthetic material like carbon-based material, for example, graphene, and also for also conducting polymer. And so now it depends on, because a lot of time, if you're talking even for battery for storage, right? So if you can replace certain component in there would make material carbon-based material, which is that you don't rely on the natural resources. And then you can at the same time come up with something that is the lightweight type of material. So you don't need to carry that heavy weight in the battery, right? Yeah. So everyone want the battery to be more compact and lighter weight. And so I think that's where material science engineering come into play. And so I think I'm sure there are research going on in that direction around the world to come up with alternative, novel, new type of material for many applications, from the battery, energy storage to energy generation. Yeah.
Thank you.
Thank you, Professor Quinn. Thank you very much. Thank you very much. We have the second project from Oanh Vũ, a junior researcher from Vietnam Korean Institute of Science and Technology. I would like to invite Oanh to introduce the topic. Oanh, are you here?
Yes.
Yeah,
Can
Oanh,
you?
we have limited time, so please be precise in your question. Thank you.
Yes. Can I share the content?
Sure.
Hello everyone. My name is Wang and I am using nanomaterial to detect cancer. As you know, that when material are in nanoscale, they exhibit a lot of unique properties that Spock doesn't have. Thanks to this property, people have created various products applied in many fields such as healthcare, medicine, environment, and industries. In my research, I create a special nanostructures for medical application, particularly for early detection of breast cancer. Cancer are usually detected by biochemistry process. The process are complex, costly, and lack of sensitivity. In contrast, my methods have been developed with more accuracy and lower cost. In my lab, I have fabricated a very special type of nanomaterial called cell iron oxide and gold nanostructure. These nanostructures have both supermagnetic and biocompatibility characteristics. In my work, these nanostructures were attacked with cancer antibody and then conjugate with a test chip. Next, we take the sample from cancer patient and drop to the test chip. Since the nanostructure is attacked with the antibody, it will bind with the biomarker of the cancer cell. And therefore, we can detect the cancer based on the magnetic signal coming from the nanostructure that we develop. It can be done easily by using our simple and made magnetic jitter. Thanks to the supermagnetic property of our nanostructure, the signal will be detected with ultra high sensitivity. Our method, therefore, can record the result quantitatively instead of qualitatively a traditional method. Since the next phase of my research will be optimizing the nanostructures to enhance the stability. And now I am trying to control the core cell structure, meaning control the thickness of the gold layer cell. And then I can study the correlation between the structure and their supermagnetic nature. I would like to receive some advice to control the thickness of gold layer better from professor. And I believe that this method will help cancer patients to improvement a lot. Thank you.
Thank you very much. Thank you very much for the research and the question. I think that, again, Professor Quinn can lead the conversation.
The question here, because you have the shell structure,
yes,
and so you have the gold inside and then the iron oxide outside. Am I correct?
Yes.
So now you have to go inside and iron oxide outside, and you for your or the opposite.
I have iron oxide inside and gold outside, and I want to control the thickness of the gold layer cell.
So can you usually depend on you if you do the reduction of the salt that contains salt gold atom, right, to grow the shell. So if you do, I'm sure there are a lot of a full body of work in the literature on controlling the gold nanoparticle and also gold nanocell. But usually you can change the reaction condition, or you can actually have the reaction run longer, and then you can try to control that thickness. I'm sure that there are a lot of people working on that area, and that you can search in the literature for that. And if you need help, let me know.
Yeah.
Yes, thank you for joining.
I agree. I think that's the most common way of creating the shell. Mm-hmm. Shell quantum dot is the quenching of the reaction. So that's the most traditional way being used for the creation of the core quantum dots.
Yeah.
Right.
Thank you for your advice. Thank you.
Okay, thank you very much. I think that our attendees have a very good question, and I would like to invite an attendee named Chữ Mạnh Hưng. Can you raise your hand, and we will invite you to ask your question directly. Yes, hello, Mr. Hưng. Can you pose your question to the speakers? Yeah. Thank you, Mr. Hưng. Thank you very much. Professor Novasolo, please.
Thank you so much for the great question. And yeah, let's start with the first part. So the question was, so we do use graphene for various types of scientific experiments in physics and chemistry, biology, and so on. Do we also use it in real life applications? And the answer is yes. So we do see the increasing use of graphene. Basically, every month there are new applications there, and it's quite likely that you touch graphene basically every day in your daily life. So it started with some very basic applications like in composite materials, either for increased strength or for the lightness, but it quite fast switched to functional composites, where you need to improve the thermal conductivity or electrical conductivity. However, probably one of the largest application these days is for thermal management. Pretty much every single phone produced by Huawei uses graphene films for thermal management, because no any other materials can give you thermal conductivity above 1000 watt meter Kelvin, and that's what is required, unfortunately, for modern electronics. And then batteries. So these days the recipes for batteries are extremely complex, and so they use, of course, nanosilicon is quite popular instead of to substitute for graphite, and but to put those nanomaterials together, they have to create quite complex interconnected networks, and it is done by utilizing carbon nanotubes and graphene to create a distributed hierarchical structure for the electrodes. And then talking about electronic applications, silicon technology is a bit challenging. So the first electronic applications which we see is the combination of silicon and graphene technology, not purely graphene, and it's mainly in photovoltaic. So one of the most sensitive photovoltaic devices are created, photodetectors. So it's for any specific wavelengths are created by combining quantum dots and graphene, and it's so former Nokia is we've got a subsidiary company on those, and that's mainly for the autonomous vehicles. So now coming to the second part of the question on the transition metal ethylcogonite. So yeah, that's very much correct, and I think we should expand this question that so graphene was the first two-dimensional material, but since then we figure it out that there is a full family of those, which includes graphene, which is a semi-metal, and then some insulators like boron nitride, and some semiconductors, right, like transition metal ethylcogonite, but there are others as well, and it is indeed quite nice that where graphene fails, for example, because of the absence of the band gap, it cannot emit light. So we have a substitution in the form of these two-dimensional semiconductors, transition metal dichrogenides, and a lot of work is done in this area, probably even more than on graphene itself. I don't think there are ready applications of transition metal dichrogenides, but what I envisage is the combination of silicon photonics and TMTCs to create optoelectronic devices to treat the telecommunication signal in the optical domains. And another one is very promising, is the quantum dots in transition metal dichrogenides for quantum telecommunication, and the quantum dots in those materials are extremely bright, so and they can be positioned and created on demand at any place of the integrated circuit. Sorry for a long answer, but indeed it's quite a rich area these days. So you cannot just review it in one minute. Sorry.
Thank you very much. Thank you very much for your answer.
Can I add just one? I can add just one example. I saw recently there a graphene transistor device that used to detect COVID virus. So that's the new one I saw the application.
Yes, and that's. I mean, we haven't spoken about the combination of the detectors and especially biological applications, because it is indeed a challenge, because all the currents in our body are ionic currents. In our electronics, it's electronic currents. So how to combine the two? You need an interface, like a sensor or something else, and graphene devices actually working really well there. There are a number of startups on this in this area.
Thank you very much. Can we just have 2 more minutes to discuss a very recent questions that coming in? People are very interested in the graphene material, which is very unique. But how about the application and the production of that in the future? And for this, I would very much like to invite Dr. Corey Hoven to give some insights. What is the main challenge in producing or applying these kind of very unique materials in the future from your industrial side?
Well, in our case, that's one of the changes we get to bring that makes life easier. Because we are printing from an ink, it's the capital costs and the production costs. In our case, it's a whole nother area. We get to use these materials to make life better. Traditionally, silicon or even thin film solar, at least they're made with very expensive processing techniques that require ultra high vacuums. The equipment is expensive, and that it's enabled by the material themselves. It's because these organic semiconductors are one-dimensional semiconductors. They exist as semiconductors in an ink by themselves as molecules. They're already that. And so when you print them as an ink, they can kind of all fall into place and become a semiconductor that's very imperfect, but it functions because they're all semiconductors. In a traditional semiconductor, all the ones on the market, they're inorganic semiconductors, and they only become but in the case of two-dimensional, but in most semiconductors in the market, they're three-dimensional semiconductors. They only become semiconductors in that three-dimensional perfect crystal. And the only real way to make them better and better is to make those crystals more and more perfect. So for us, it's making our life way easier. We can enable this technology to fit in a supply chain where it needs to, only because this, brand new technology came out, and they did all this research in laboratories at universities, and people were innovative, and that enabled this.
Yeah, thank you very much, Corey. I know that we are very short in time, but there's a high school student that came in just for one very, very exciting question and very good, care for the people. She asked how to give disadvantaged people access to new technology that will be used for renewable. Please, Professor Quinn, can you take this lead?
Yeah. That's a very important question. And any technology that, if we think about that can reach to many, the large population, especially the farmer, the worker, the poor people. And so we believe that sometimes the organic solar cell and newer solar cell technology, something Corey mentioned that require a solution process. You don't need the clean room and expensive technology. That will be a way to go. So imagine if you can buy this, instead of silicon solar cell module, you can buy the organic one, flexible, for a fraction of that cost. And that will be the way to go. Yeah.
Thank you very much. This answer has brought us to the end of this very interesting public dialogue. We believe that you enjoyed the conversation with our keynote speakers, and we believe that this dialogue has enriched your comprehension about energy and materials. I would like to thank you very much, the keynote speakers, for your tremendous contribution and engagement. I would like to thank our VinFuture team for putting this event together with very hard work. And I would like very much to thank the audience for your engagement and spending time with us. We hope to see you next time. But for now, from me, Manan, and the team, it's goodbye.
Thank you.
Thank you so much. Thank you.
Thank you, everyone.
Thank you so much.
Thank you. Thank you, everyone. Thank you so much. Thank you.